All right, I think we got to go. Yeah, it's working. Well, happy Tuesday. Sorry for the trouble here. We're back on the Wi-Fi. I don't know what happened to that. And we're done with break. We're back. I guess slightly more than halfway, right? Because break was just after the halfway mark or so. So week 10 of 16, and then the final project. The whole schedule is a little weird here, but so we're going to talk about priority queues this week, and then we'll do our lab next Tuesday on priority queues. Maps, hash tables, skip lists. We're actually going to mostly skip over skip lists, funny enough. Maps and hash tables, we'll get into some basics, not super deep on those. We'll look at how we can build our own. And then we'll come back to binary trees, looking at search trees. So we talked about trees, we talked about binary trees. Then we're going to skip them for a little while, and we'll come back to them. And then some basics on sorting and selection. And then talk about ethics, which is really cool. We include because you can do some sketchy stuff with data and with software. So definitely good to spend time on that. And then we'll get into final project work time the last couple sessions. So we kind of power through a little quick to make sure we've got time at the end for you folks to work together. Now, this last project does need to be with partners as part of a team. If we need to do one team of 3, I'm okay with that, but generally there's not too much to do for 3 people. It's better off with pairs. It's a lot easier to try and meet with just one other person too. Back to my friend, thanks for donating those bits to the Student Scholarship Fund here at the University of Michigan Dearborn College of Engineering and Computer Science. So we'll have time to do that in case you can't meet at other times. We've got this class time set aside for that. So the last lab on 418 as well will just be group project, final project work time. So that lab will be around. I can answer questions, get you pointed in the right direction, that sort of thing. And then instead of a final exam, you will just present your project. You'll run it, show the results. Usually it's a lot of fun. It's pretty quick. It's 5 minutes or so per presentation. Right? It just goes pretty quick. It's not a big thing. You don't need a PowerPoint or anything like that. We just run the code, show that it works, talk through it real quick if there's any questions. And it's fun to see how everyone approaches it differently, which is cool. Okay, that's the plan for March and April, believe it or not. And then we'll get into summer. All right, awesome. So let me fire up PyCharm here. So with a priority queue, we actually build on some of the work we did with trees. And we never finished. The lab had us implement a tree with the array structure. We're working on that. And some of that, the arithmetic of how do I get from, well, what is my parent's index? I have to double that and then add 1 or add 2, depending if I'm the left or the right child. So we had a lot of that. We had the linked version in the book with mostly a copy paste. Again, some of the changes because we're not using the inheritance. This is week 10. I don't remember. Yeah, week 10 priority queues. The queues. So we're going to build off of that. When we talked about trees and this idea, the structure of trees and how we can represent them in an array-based storage area, and we talked about trees that are full or complete. Does that ring any bells? I know it's been a while now. So the idea with a full tree is every level has all of the children, and then there's no hanging at the end. It's just you either have 2 children or no children, and the last level has no children at all. Right? So a complete tree is like that, but then you start adding the children to the farthest left position, and the next furthest left, and the next furthest left, and the next furthest left. So that makes a complete tree. It's mostly full, and that very last level of children is all the way to the left, as far possible as you can go. And why that's important is that's how we store things in a priority queue. We keep ourselves in this sort of complete structure so that we are as efficiently stored as possible. Because you're able to store at every level, right, double the number from before, the way we manage this. So when we have our array-based storage, if we're not that big old link of I just have 1 child and 1 child and 1 child and 1 child and 1 child, that's really inefficient to store in an array. But if we're filling up every level as we go, it fits very well in here. So let me grab a word. I have my mouse today, which is super nice because it's really nice to have a mouse. So we have our first level, right? It has its children with the next level, and on and on and on. This is an efficient way to store these with that array-based storage here. And we can keep on adding levels. So what we're going to do with a priority queue is we're going to store all of our data in an array-based binary tree. And as we add data, what needs to happen with the priority queue is it's sort of like the emergency room, right? The highest priority should go see the doctor first. If you go in and you have the flu, you're probably going to be behind somebody who has a heart attack, right? If someone comes with a heart attack, they're going to get seen before you with the flu, that sort of thing. So we prioritize these things. So for the priority queue to work, you need the highest priority to be at the top. And that's the easiest one to grab. If we think of how you can get at items in a tree structure, it's really easy to get at the root because it's right there. You know what the root is. To navigate the rest of it, you kind of have to go through all these child relations, and that takes a little while here. So we want the highest priority item to be at the top, and you can either do the highest priority or the lowest priority. It's called a min or max priority queue. Right? Max priority queue keeps the highest item at the top. Min priority queue keeps the smallest item at the top. However we want to say we want to compare these things, we'll keep them at the top. So what happens here is there's a process of when you go and add a value, you need to go find where the correct location is for it here as we add in values to our tree. So as we just start adding in values, we'll find the next available spot here to keep that complete form. And then we do this cool process called upheaping, which is one of my favorite technical terms. So we have to find where it goes up in the heap. So we call this kind of like a heap of values here. And the rule is, and this is for like a max, that's an A there, a max queue is you have to be more than your children. That's the only rule. As long as you're more than your children, you're good. So the highest value should be here at the top here. So maybe we'll say like this is 77 up at the top here. Right, we've got 77. So as long as they're more than our children, we'll be okay. And then as we start adding values, we need to make sure that they go up into this heap structure until it is no longer more than its parent. So let me pick some other, I should maybe start a little smaller here, this will be easier. So if we have like 23 and 15 and 20 here. If I want to go add another value, right? So right now I just have the three values. Why is it still like, they're all like highlighted. There it goes. It looks really weird. So if I want to go add another value, I'm going to add it to the next available spot here. So this will be hanging off of this child here, right, starting the next level. So what number should we add? It can be any number. 9. Okay. So we'll put a 9 in here. We'll say, are you greater than your parent? No? Okay, we're done. So nothing has to change. Let's add another value. 5 from chat here. We'll add a 5. Are you greater than your parent? No? Okay, nothing has to change. Let's add another value. 21. Are we greater than our parent? We are. All right, so now we need to swap. Right? If we're greater than our parent, we have to trade places. So we're going to swap the 20 and the 21 here. So we'll put 21 here, put 20 down here. And then we keep this process going. This is a recursive process where we don't know how many levels are in our tree right now, right? It doesn't matter how many, if I've got 50 levels, or if I have 5 levels, or just 2 levels here, right? As I'm upheaping myself here, I need to keep looking at my parent, and I need to keep going until I am no longer greater than my parent. So we're going to look again. Are you greater than your parent? No. Okay. So we stop. All right. Let's add another one. Add one that's bigger than 23. That's a number. We'll make a new largest value here. 25. Okay, so we'll put a 25 here. We'll say, okay, are we greater than our parent? Yes, we need to swap. Okay, easy. So we'll put 25 up here. This now becomes 21. 21. And then we're going to repeat. Are we greater than our parent? Yeah, okay, so we swap. So this becomes a 23. And we put the 25 up here. Now, imagine in terms of n items in this structure. Because everything we're looking at performance-wise is kind of, based on how many items I have. What's my O of n? Or what is my performance here based on how many n items I have? Well, to add an item then, we have to upheap. The worst possible case is you add the biggest item and has to upheap and upheap and upheap and upheap every single level. But thanks to this being this cool powers of 2 thing, that works out to be O of log n. right? Because we have to get this logarithmic structure where every next level is half as many as it was before. So with as many items as I have, right, it grows logarithmically. Logarithmically? I think that's the right word, right? Because every next level I get to double the number of items from the level before. So to add something here works out really fast. Now to look at the highest value. So like the idea, like with a stack, you could peek, or with the queue, you could get the front value without actually removing it. So if we just looked at the max value here, what's the performance to get the max value out of our max priority queue? Well, it's constant. That's just O of 1 because it's at the top. We don't have to look at anything. It's not sorted, but it's in this max heap form. So we know the largest value is at the top. So that's a constant lookup real fast. Now to remove that top item here, I'm blanking on what the function is for. We'll look up, see what the book calls it here. But to remove that item, now there's another fun process we're going to do here. So if I wanted to remove the max item, what I'm going to do is I'm going to take it off here. So we'll take off the 25, and we end up swapping it with the last item in the tree. So the furthest child to the right, the last item that we have, goes up here. And now, instead of upheaping, we start downheaping. We take this value and start putting it down in the structure. And the rule is, if we have a child larger than us, we swap with the largest child. Now, if we're smaller than both children, we still want to swap with the largest child. So we don't just immediately say, hey, so if this was like 12, we wouldn't say, hey, 15 is bigger than 12, let's swap 15, because 15 can't be a parent of 23, right? So you have to find your largest child and swap with the largest child. So we'll just swap. So we'll say, okay, now we start downheaping. So we'll take the value off, hold on to it, and swap our smallest last value in there back to the front and start downheaping it. Okay, so we'll swap with 23. 21 and 23 swap places, 23, 21, and we keep on downheaping. Do you have a smaller child? Do you have a smaller child? Do you have a smaller child? We're done because our child now is not larger than us. I'm sorry, do you have a larger child, right? So we've downheaped as far as we need to go. So if we were to remove 23, right, we'll go take that one off, and then we'll swap with the 20. Put the 20 up here. We start downheaping. Sure, okay, well, we're going to swap again over here. Now we have 21 and 20. All right, we'll take the next one. All right, so we'll take 21. That becomes the 5 here. 5 comes off over here, and we start downheaping. All right, sure, let's swap with our smallest, the largest child. So this becomes the 20. The 5 goes over here. Okay, we want to take the 20, sure. And we swap with the 9, put the 9 at the top. Now 9 has to downheap, we're going to swap with 15, right? So that we get 15 and 9. Oh, erase those ones here. Right? And again, and again, and again, and again. We just keep on downheaping these items as we swap them. So the furthest that it's going to have to downheap is if that was the smallest value, we put it at the top, and now has to work its way all the way back down the levels. Again, is log of n to remove something. We get really fast adding and removing because logarithmic of n is actually really good. And that's a really good performance. Now it's not constant. Constant's the best. But in terms of if I've got a million items, if I can take the log of a million, that's a lot faster than doing something a million times, right? So if we just imagine we just had our list or our, whether or not it was a linked list or an array-based list, here, if I wanted to find the largest item, I'd have to go look at all n items and say which is the largest, right? Because I have no way of knowing which one it is until I have looked at every single item. So finding the max here is really quick if we keep it in this structure. That's the sort of the idea here. So we're going to go and steal our binary tree code here. So I think we've got a binary tree. Did I start the lab code? What is it, lab? I think I started it, but I don't. Did I commit it? Is this lab 6? This is the linked binary tree. Shoot. So this one has all the functions that we need in it. That's going to be obnoxious. That's fine. That's not going to do what we need here. Should we cheat real quick and go? Because it's not the having the array-based binary tree is not the important part. It's using it becomes much more interesting. Is that okay? We go borrow some code. We're going to go ask the chat bot here. Nope, chat. All right, so write a array-based tree in Python. Let's see what we get here from chatbot. Oh, it's thinking real hard about it. This is probably faster than I can type. So if you're the left, 2 times your index plus 1. If you're the right, 2 times your index plus 2. Cool. So let's try this here. And we're going to cite our source here, right? ChatGPT, and we'll include our prompts. We talked about this? Did we not talk about this? Sometimes I forget who I talk to. So ChatGPT is amazing. Does some cool stuff. Okay, if we have not talked about it, then I'm sorry. I am behind. So a couple rules. I think I posted this in the Discord channel here. I'm trying to remember what it was. ChatGPT. There's a really good chart here. No, not workflow. Chart. To you. I think this is it. This one had a really good Twitter image. This one? No. I'm gonna have to go find it now. Oh goodness. All right, give me 1 second. This is worthwhile here. I promise. Yeah, let me put the screen on for a second. I don't know what's in Discord at the moment. Come on. There we go. I think it was interesting stuff. Yeah, this was a while back. This one? No? This one. Here we go. Okay, I found it. All right. Here is the flowchart. Is it safe to use ChatGPT for your task? And that's a little small here. At least can I make that bigger if I go to the website? There. Is that a little cleaner, I think? So first, does it matter if the output is true? No? Then go ahead and use it. Nobody cares. If it matters if it's true, yes. Do you have the expertise to verify that the output is accurate? This is the important triangle decision point here, right? Especially when you're asking it to write code. Do you have the expertise to make sure that the code it writes is correct? Because ChatGPT is a prose machine. It's an imitation machine. It's not an answers bot. It's not going out and verifying it does things right. It's going out and giving you something that looks like the right answer. And a lot of times it is, but not always. So do you have the expertise to verify it's correct? Yes? Okay. And then are you able and willing to take full responsibility, legal, moral, etc., for missed inaccuracies? Yes? Okay, maybe it's possible to use it for your task. If no, don't do it. Right? And when we get to ethics, we'll talk more about this, which is interesting. But the physical engineering disciplines, like civil engineering, the lead engineer for a bridge that gets built has personal liability for that bridge. If they fail to follow best engineering practices and the bridge fails, they're personally liable. We don't have that for software. It's a little weird, but we don't. Maybe we should. I don't know. That's an interesting ethical debate at some point here. And there's all sorts of interesting case studies on when you write software and it screws up and hurts someone. There's lots of examples, unfortunately, of this happening. So it's one of the reasons that software engineering is a specific discipline rather than just computer science. Like the idea of applying engineering principles and engineering processes to writing software gives you these extra benefits because the people who have done engineering for a long time have learned to do these steps and have these things in place to make sure that the things that they're building, generally physical things, right, do the things that they're supposed to do. So it's a little weird to adopt it sometimes for software, that we're not building physical things, but a lot of those practices have been adopted, and that's what we call software engineering. And that's what I'm a big fan of as well. So data science is cool, but applying engineering principles is awesome. So if you're able to expect responsibility. So in your case, right, as a student, do you know if it's actually going to do what it's supposed to do? That one's kind of tricky, right? Because we're kind of learning some of these things as we go. So we can test it, right? Just like when we write our own code, we can test it. Does it do what I expect it to do? Yeah, if we test it and it knows what it's supposed to do, we have a pretty good feeling that it's doing it correctly, right? That's our check. And that's the expertise we have, is I can throw things at it and see if it works, right? So sure, we can do that. And then are you willing to take responsibility for it? Right? If it doesn't do what it's supposed to do, well, that's you. If you turn it in, right, you're putting your name on it, even though we're citing a source here. And with ChatGPT, there's no URL. Like with Google, right, you can put in your query term. It like shows up in the string. Right? Have you seen that? Like if you do, I like things that give me free coffee. It shows up here, search, and then this question mark Q. That's the query that you give it. So like this URL includes your question, your prompt. ChatGPT doesn't do that. So if you're going to use ChatGPT for something, ChatGPT, it's lost all meaning now. Just include the question that you've asked it, the prompt here, because that's really the only thing we can do. And most of the time, it gives you the same answer. You're able to do interesting things to make it give you different answers, and it doesn't always give you the exact same answer. If you repeat this, most of the time you'll get it, but depending on what you fed it, it can give you different results. So it's not going to be perfect. And it keeps these conversations and remembers conversations, and you can do all sorts of fun stuff. So, but I'll say this from ChatGPT. Here's the prompt. We okay so far? All right, cool. So we can get the left child index, we can get the right child index. Great. So we are able to store values in our binary tree here, right, based on the values. Now the problem is I can't get to my parent node though, so we need to ask for that, right? So can we add a function, get the parent index? We'll see if we can do that for us. I don't want the whole thing again. We're going a little faster this time. There we go. So index -1 floor divided by 2 should reverse the +1 or +2, right? Because we're subtracting the 1 and then we're floor dividing. So if it was +2 and we've only taken 1 away, but you floor divide, you lose that half anyway. So this should give us the correct one here for us. We can go and add that in. And again, this was another prompt here, right? ChatGPT. So specifically, right, we added another question. So we'll go and cite this one here. Keeps adding my name there. I must be copying wrong. Okay, so we can get the parent index. And again, it's all based on whether or not we're less than the length. You get the actual value out, otherwise you get back none. So we have to check to see if we got a none or not. So if you don't have a left child and you ask for the left child index, we're going to get back a none, and that's okay. We're going to check for that in a little bit as we start doing this thing here. Okay, so this is our binary tree. But we don't actually need to be a binary tree. We want to be a priority queue, right? So we're going to change this up here, right? This was our base. Now we could wrap around this and have a binary tree as a property and start adding values to it and doing all those sorts of things, but that's probably a little more trouble than we want it to be. So we can just change this to be a priority queue, right? And then add adapted. Because we took their code, we're changing. So we'll be a priority queue. So I have a bunch of nodes. Now we don't need this values thing here. I don't think there's a better way to go about this that the book gets into. That's probably a little more interesting than we care. And that's okay. So we've got the number of nodes. Great. We can add a node. We can now adding a node is not the end of the process here, right? And this is going to be our max priority queue, right? We want to keep the highest item at the top. So we add something. We'll just say add, maybe add a value. We'll add it in here, and then we need to start that upheaping process. right? So then we're going to have, now the upheaping process is not a public function. No one else needs to be able to call upheap. So this will be a private function, right? So we'll indicate that with our underscore. This is upheap, and you have to give it the index, right? Where are we upheaping from, right? So once we add a node, then we're going to call self.upheap given the index. So the index of something we just added is going to be the length of self.nodes minus 1, right? If I have 5 items, right, the last index there is 4, right? Because we always start at 0. So we'll upheap from here. That's our add process. So now to upheap something, right, we need to see, is my parent large? Am I larger than my parent, right? So if the self.nodes at the index is greater than self.nodes at what index? Well, it's going to be the index of getting my parent index from me, right? Because that will give me an index value back if it's not none. Okay, so maybe we got to pause for a second here. So we'll get the parent index. Parent index is going to be self.get parent index from my index. And probably with these ones too, these can probably all be private as well, right? Because no one needs to do these directly working with the priority queue. We're going to mark all those ones as private, right? And we're not going to get anything directly either. I don't think we need that one because we don't use a direct get. All right, so we're going to get the parent index from our index. And then if the parent index is not none, we want to keep on going, right? Because if I get back none, right, that means index of 0, there is no parent for 0. We're done. Otherwise, we'll have a parent here. Excuse me. So if it's not none, now we can go and get, if I'm greater than the value at my parent's index, we need to swap, right? So to swap, now usually we swap with 3 lines. Python lets us cheat because it's really fancy. I prefer the 3 lines because I always get confused with the other version here, but Python lets you say self.nodes at index, comma, self.nodes at parent index is equal to this way backwards. And this is crazy. This one always drives me nuts, but that's okay. It's a fun shortcut. On this one. So you can say this, and Python will swap them for you. This is not very intuitive, so I don't like this approach here, right? The easier way here, you'd say like, hey, I want a temp value is self nodes at index, and then we can say self node at index is equal self nodes at the parent, and then self parent then becomes the temp here, right? So still what we were, take what we were with, replace it with our parent, replace the parent with what we were. Right? This is how we would usually do that with 3 lines. Python lets you do this with 1 line. And most people say that's better. I just find it confusing, but that's just me. Does that make sense? Okay, cool. So great, we'll swap. Then if we've swapped, we're going to call self upheap again. Upheap given my parent index. Because now my value is at my parent's index. Right? We've just swapped, I've put myself in my parent's place. We need to upheap from there and then keep on going with this recursive process until parent index is not none or we're not greater here. And really you can combine these, which is nice. So if it's not none, and I'm greater than, and then all this can get untabbed. This way your code isn't like 4 tabs in. The more tabs you have, usually the uglier it is. So if we can reduce that, might as well. Right? Because if it is none, then this whole thing stops because we're anding. It's false and we're done. Game over. Right? We're done upheaping. Or we can check to see if we're greater than. That make sense so far? Typo in word upheap. No, upheap is fine. And self nodes should actually probably be private as well. We don't want anyone accessing this. I'm going to refactor rename to private nodes here, just for a little better habit here. Okay, and then we could probably also add a length function. Nope, that's underscore length. Right, this is the special length function. We can return the length of self nodes. Right, I think we've done the is empty before as well. Is empty. Return length of self.nodes equals 0. Right, if we're empty, our length is 0. If it's not 0, then we're not empty. Just a little shortcut here. Could even just say self too. I guess that's fine. Either way should be okay. Hey Ernestin, thanks for dropping in by. All right, so that's the upheaping process. So when we add a node, We'll add it to the end and upheap it. Great. Then we want to, what do we want to call this? The priority queue get max, or get or remove max or something. Oh, we should look that one up. Priority queue remove function name. I guess it's just called remove. Okay, priority queue. Sure, we'll call it remove. That's the wrong one. Remove. So if we're empty, we should raise an error first, right? So that's a quick step. So self is empty. We can raise a value error. Priority queue is empty. Priority queue is empty. Otherwise, we can go remove. So we'll get the value, right? It's going to be my self.nodes at 0. That's the first item, right? We know it's the first item because it's at the top of how we're storing things in our array-based storage. We'll have that. We need to hold on to that because now we're going to start swapping things, okay? Then we're going to put in this place the old last item here. So then my self.nodes at 0 now can equal self.nodes at the length of self.nodes minus 1. Right, that's the last item, right? The length minus 1 should be the last index. We'll go get that. Now, the important thing here, if we're using values that are references, right, just numeric values are nice and easy. But if the value is a reference somewhere, we need to make sure we have cleared that out. So I'm going to take this here, and we're going to assign it none to get rid of it, to clear it out. The other thing we can do is just pop it off too. We can take our self.nodes and call pop to remove it. Now we're not going to do anything with that value at all, right? Or we can just grab it right here and assign it back, save ourselves a little bit of time, because pop will take the last value and remove it for us. So we're kind of doing the shortcut here. We don't need to do more work than we need to because a Python list is amazing. Other languages, you have to do a lot more work, but Python lists are fantastic. So we'll just put it here, and then we'll start downheaping. So we'll call self.downheap given 0. Right? So we need a private function for downheap. Define downheap given an index. Now remember, the rule for downheap is we need to swap with our largest child. Right? So we need to get both children. If they're not none, then we need to swap with the largest one. If one of them is none, well, we only have one child, and if we're larger, or if the child is larger, we swap. Right? If we're already larger than our children, there's no swapping, or if we have no children, there's no swapping. So there's a lot of different cases that happen here. So we'll get the left child index is going to be self.get left child index of our index. Now, because we're a priority queue and we're keeping ourselves in this complete form, if I don't have a left child, there is no right child. It can't happen, right? Because we're never in the place where we have a right child but not a left, because that would not be the complete form. It means there's a gap somewhere. We can't have that. So if my left child index is none, we're done, right? So really, if it's not none, then we want to keep on going. Is not none, sorry. So if it's not none, then we can go and look for a right child index. So we'll get the right child index, self.get right child index, given my index. Now we need to see if that one's not none, right? So if the right child index is not none, then I'm going to get now a smallest child index. And it might actually be easier to just rename this here. So we can assume the left is the smallest until we know otherwise. So let's rename this one here. We'll say this is going to be my smallest child index. Right? We'll assume that's the left. If it's not none, we'll look at the right. And then if the right is not none, and then, I'm sorry, we want, we're downheap, we want the largest. So this should be the largest child index. I'm backwards. Not the largest child index. Oh, goodness. Refactor, rename. Refactor, rename. Largest child index. Okay. Nope. I already had the S. Okay, largest child index. So if the right child index is not none, and it's bigger than the left child index. So if self.nodes at the largest child index is, I should say this one's greater than, right? So self.nodes at the right child index is greater than self.nodes at the largest child index. Because we'll assume left is the largest until we know we have a right and we see that the right is bigger. So if we have a right and the right is bigger, then my largest child index is going to be my right child index. Right? Again, just trying to do some shortcuts here. So now I know which one is the largest, because if it's not none, great. I have a left, that's now the largest. If I have a right, great. Now let's compare which one is actually larger here. Right, so now we have the largest child index. Once we have the largest child index, we're going to swap. Right, again, so we'll say temp self.nodes at the index. Then we can assign self nodes at index, right? Swap with our child, self.nodes at the largest child index. So now we've put the largest child in my place, and now I need to put myself, the temp value, back in my child's place. If we had to swap, now we recurse, right? If we didn't have a child, we're done. Oh, actually, we missed another case here, right? So this is if self.nodes at index is less than self.nodes at the largest child index, right? We're only swapping if we're less than, right? If my child's bigger than me, I have to swap. Right? That's an important piece here. Otherwise, we just swap all the way down and forget to look. Okay, so if we did swap, then we're going to recurse. So self.downheap given my largest child index, because that's where my value is now. We need to keep this process going to keep on downheaping as far down as I need to go. Right? And then define, what is it? I don't know, get max. Just return self.nodes at 0. So we can get the max value. We said that's constant time. Removing something is going to be log of n, because, oh, and when we're done, we'll return value. Right? After we've downheaped, we can return the value. We got to make sure we return. Right? To remove that, downheaping, it might only take one operation. Maybe. It depends on the structure, you know, what values we have here. At worst, though, it's going to take log of n as it goes down level by level by level by level, finding where it needs to live here. Cool. So if we have a bunch of values and I wanted to throw them into a priority queue and pull them back out, I can get them in sorted order, essentially. So if I have n values and I want to go through, so if we look at these, so add here, right, we said was going to be O of log n, right, and then remove, we said O was O of log n as well, O of log n. So if I have to do something n times, and it takes log n to do it, that's n log n, so n times log n, and n times log n. So to get a bunch of values and get them, put them in, and then take them back out in sorted order, it's 2n log n. And we throw away coefficients, so I could use a priority queue to sort values in n log n time. Not the worst here, but when we get to sorting and selection here, so sort performance, I don't know. We let's sort common sort algorithm performance. Here we go. Where's a good page? Sorting algorithm on Wikipedia. Where's our? Here we go. So quick sort and log n. How's it going? Merge sort and log n. This is average time here. Again, this is mostly what we care about. Best case rarely ever happens. Worst case is important. So quick sort can perform really badly, turns out, which is interesting. We don't actually get into quick sort. We'll talk about it. It's in the book, but that's, you'll typically get into that sort of thing in 350 algorithms analysis, data structures and algorithms analysis. So we're just kind of introing the topic here. In place merge sort, a heap sort. Remember we mentioned this idea of heaping, up heap and down heap? We're using a heap. That's what we're doing here. So you can use a heap to sort in n log n time, worst case and average case. Right? So this is kind of a fun, it's all sorts of cool sorting ways you can do things here, which is fun. There's a really cool YouTube video that someone did that puts sound to it happening, which is fun. Ooh, this is cool. You can like look at all the different sorts. Yeah. Anyway, so a bunch of ways you can sort using a priority queue structure. And again, this one is a max priority queue. Right? If we wanted to change it to a minimum priority queue, we really have to change like some less than signs to greater than signs, or greater than signs to less than signs. That's about it, right? We're just if I'm less than versus if I'm bigger than. Just in two places here, right? Not too bad. Okay. So I think our priority queue is done, right? Based off of a binary tree, array-based binary tree, right? Oh, that should be and. I said a, but ChatGPT didn't mind. I guess it can deal with bad grammar. All right, so we want to try it and see if it works, right? So this is our main file. We probably should have put this in its own. Let's put this in its own class here, right? Because that's probably better. So let's go add a new Python file. This will be max priority queue. There we go. And then in main, now we can import it, right? So from max priority queue, import max priority queue. So we'll make a priority queue. So let's make some values here, right? So we want a bunch of random numbers. So for value in range, I don't know, let's do like 100. We want random, oh my goodness, random values is a list. We'll take our random values, we'll append random.randint. What do you want, like 1 to 1,000, 1 to 10,000? Duplicates are okay, actually, which gets to be interesting because you can have two of the same number. Right? If you're not greater than, you're not going to upheap, but you'll probably be a child. So as long as you're not greater than your parent, you're okay. So if we get some duplicates, it should be okay. We'll do 1 to 1,000. We'll throw 100 values in there. And then when we're done, let's go put them in a priority queue. Right? This way, we'll store them in the do we even need to store them in a list? Should we just add them right to our priority queue? Yeah, we can do that. So we'll make a priority queue over here. So here's our max priority queue equals a max priority queue. Oops. And then we'll just call add. Right? Add a value. Right? And then we can say while my max priority queue is empty, and while we're not empty, right? Well, it can print the max priority queue dot remove. Remove the value and print it. Remove the value and print it. Remove the value and print it. So this should remove all 100 here. Let's see if it works. Right? So we should get largest to smallest if our code worked here. All right, I'm really worried here because we'll see if it actually worked. It looks good so far. Oh goodness. Uh-oh. All right. Well, it failed at some point in here, popping list assignment in. Oh, so once we pop, we can't put it at 0 because once we've popped the value, it's gone. Right, for that very last item. I think this is the last time that ran. It feels like that's the last time it ran here. So we can add in one last check, I guess. So if length of self dot nodes is 1, we can just return self nodes pop. That's that like edge case here, right? To make sure that if we only have the one item left, once I pop it off, there is no index 0 to assign it back to. Does that make sense? So it's like a little safety check for us here. I think that'll work now. Okay. Cool, that worked without errors. All right, so one bug, right? So we tested it. Again, not a good proper test, but that's okay. We could write some proper tests later. We're just kind of eyeballing it here. So 999, 998, 997. Wow, you got like the top 4 numbers here. Random values. What, out of 1,000? I don't know. Is that interesting? What are the odds of that? All right, they seem to be in descending order. And here's some duplicates. Look at that. We even found some duplicates coming out in the right order. Seems to be okay. Seems to be okay. We're just eyeballing it here, but I think it worked. Did it work? Very cool. How do you feel about priority queues? Does that make sense? And why we use the array-based binary tree storage? Because it stores it very efficiently, right? And Python lists are great. They'll just expand for us here. So if we had to expand at some point, even when we're adding a value, right? So the worst case performance then for add technically would be O of n, because it has to go and add and copy over. Remember back when we did our array-based lists? The worst case here, but our average, right? We should specify this as average here, right? Average here is O of log n, because amortize that performance across all the other calls and all that fun stuff we talked about before we forgot it, and that's okay. You don't have to keep it in your head. So average performance we should specify here for these. O of log n works out pretty well. Questions, thoughts? So priority queues are really cool because we can use them in places where they make sense. Again, just like a stack or just like a regular queue, if it fits the problem we're solving, it can be useful. You don't use a priority queue everywhere, but they're nice to have there if you need to solve a problem that depends on, hey, I want to put these in and deal with them in some specific order, or deal with the priority queue, right? Again, things like the emergency room, pretty common. You can use a priority queue for things like the fast pass line. And when you go to Disney now, you can pay to jump the line because they figured out they can make money off of that. They used to give it away for free, and you could get like 3 a day, and now you have to pay for them because they're like, hey, people will pay money for this. Sure. It sucks though because I was not going to pay for 7 of my kids to jump the line. Like if you go like one kid, I can see it being worthwhile. But anyway, that's a big family problem. So if you have the fast line with one priority and the regular line with another priority, right? You can then merge them in as you go, and that's kind of what they do, right? You get put in like 10 people back or 20 people back. You jump most of the line, but not quite all of it here as you go. So there's like 2 different lines going. You can pull the high priority people, and they'll kind of space them in and out. They try at least to have it not be so blatant that they just cut the line, but it is what it is. I think Cedar Point does this too, right? It's been a while since I went to Cedar Point, but they have the fast lane there. Last time I went, do you guys go to Cedar Point? No. Now that I'm old, I can't do the roller coasters that have like big spins anymore. I almost blacked out on the one. It was really bad. As a kid, it was great. It's like, yeah, spin me around a bunch, but no, almost blacking out was not a very comfortable experience. So I did not ride that roller coaster again. My son doesn't like roller coasters either. I don't know. But so anyway, depending on what problem you want to solve, you can use this. This is one of the tools we have to solving problems, which is fun. So when we get to our lab, we'll go and look at how we could solve some silly problem with the max priority queue, kind of simulate that here. We actually got a lot further along than I thought. I guess building out that array-based storage here, this was definitely saved a little bit of time. I think we knew some of this arithmetic. We talked about this last time, but this saves a little bit of time for us here with the ChatGPT. So let's see, what else do we have? Is that all we had this week was priority queues? I think it was. Oh, goodness. Let me see what else Chapter 9 has, because there's some other cool stuff we didn't really get into. 3. Let's see what else was in Chapter 9. Oops. So general trees. Yeah, implementing it. He spends a bunch of time showing you a bad way to do it. I guess it's interesting. You can make a priority queue with an unsorted list, where to find the smallest item, you have to go through and find the smallest or the largest item in that list. I didn't find that particularly interesting. Or if you have a list that is sorted, you can do that as well. But the performance of putting things in sorted order gets to be a little tricky here. So the heap structure is useful. Yeah, the array-based representation of a complete binary tree. That's what we did, right? I think before, when you read these words, it probably sounded like gibberish. If you tell someone you were studying an array-based representation of a complete binary tree, they'll look at you funny. It's kind of worth it sometimes, though, just to like make people look, you nerd. I don't know. We get into this because we're nerds, right? You got to embrace the nerd. No? Okay. Python heap, priority queue. The bottom-up heap construction. This one's really cool here. So if you know the values already, you can get better performance by building the last level first, and then the higher level and the higher level and the higher level. And he goes through some of the math behind that. That's probably one of the more advanced topics you can pick up in the next class, but that's a cool trick someone who's really smart found out. Okay, we can make this even faster, which is cool. And then doing sorts with a priority queue and comparing with some certain sorts here. We looked at, we'll talk more about those specific sorts later. And then you can kind of make them adaptable if you really want, where you have these locators, these idea of like positions. Yeah, it's again probably a little more abstract little more advanced than we need. So yeah, that went pretty well. Went pretty quick. We've got a project to do soon, right? When does that one due? Our stacks and queues. I was due today. Okay, that's why we have so much extra time. So let's did you all get it in on time? I didn't even forget to ask. I know my power was gone for like almost a week between those 2 power outages, so I got nothing done. That was awful. On Thursday we'll talk about the stacks and queues project then, and then we'll just do the review of that, and then we'll talk about the next or the final project. So the last individual project we're going to do for the next 2 weeks, and then that'll put us out to about week 12 or so, and then we can start on the final project on week 12, and you'll have 13, 14, 15, 16 to work on it. And ideally, and my goal is that on 418 you're done. I would love it if you folks were done with your project on 418, so you had nothing else to worry about for your finals, and you can focus on your other classes, because I know you have other lives, other things going on in your life. You probably don't have other lives. But if you can get it done by 418, hopefully we'll have enough time. These last 3 sessions, I can float around, answer questions just for you folks, and the last lab time as well, just reserved for final project work time, so that you're feeling good about presentations going into it. You should know, hey, I'm going to get 100%. This is great. We can go from there. So So Thursday we'll talk about the project. So if you needed a little extra time, or if it wasn't quite where you wanted it to be, feel free to do some more tweaks if you need it up till then. So we'll talk about that on Thursday. Okay, cool. Well, thanks, folks. Welcome on back. Happy March, and hopefully it stays sunny. Thanks for hanging on the line, folks. See you around.